Bom dia. A very good day to all. Thank you very much for continuing with us. I hope you are enjoying the talks and having a pleasant time so far. Today is the last day, but I'm sure it will be a great day. And I'm very happy to introduce the first speaker, André Belotto da Silva from Aix-Marseille University. André, I will continue a little bit with your presentation. André's academic trajectory started in this university, Universidade de São Paulo, where he did his undergraduate and master's studies. Then he went to France for his PhD that he did with Daniel Panazzolo at Haute Alsace University. And after his PhD, he held postdoc positions in Toronto and in Toulouse. André is a very young mathematician, but he has already a solid and very original contribution to singularities of varieties, differential forms, foliations, and metrics. So thank you very much, André, and you may start your talk. Please, thank you very much.
Oh, thanks a lot. Thanks a lot for this very kind introduction, and thanks for first of all for you, Cidinha, and for all the organizers and organizing committee for the opportunity to talk about my work. So, without further ado, I'm going to talk about a new proof of Gabrielov's rank theorem. So, the subject of today's talk is a classical theorem, or a fundamental theorem, better to say. It's not as classical, in local analytic geometry. And it's a theorem which was proved by Gabrielov in the 70s, but whose original proof is considered to be very, very difficult, and that in the proof should contain ideas and ideas to be developed. That was kind of the impression that the community had, that there were ideas hidden in it that we could develop in a more abundant way. So this is a work in collaboration with Octave Cormy, which he was a postdoc in Marseille, and I was a postdoc in Budapest, and Guillaume Hon, which is a colleague here from Aix-Marseille. And our initial objective was to clarify the proof and to develop these techniques, to see if we could develop certain of these techniques. Okay, so I'm going to talk a little bit, well, just before jumping to actually the talk itself, I'm going to focus a lot on the proof itself, because we feel that this is an important part of our work. It's an important part to tell that, to try to communicate that we feel that we have clarified the proof, and to communicate how, right? And to give emphasis, to highlight to what kind of technique it appeared, and what kind of new techniques it appeared. Okay. So what is the topic of the talk? The topic of the talk is local analytic morphisms. So for us, K is the field of real or complex numbers. At some point, it's going to just be the complex. But for now, we consider the real and complex. We'll consider germs of analytic mappings. So these are just mappings from Qm, with some dimension m, to Qn. So a priori, I'm going to assume that everything is smooth. Like not the mapping, but the source and the target are smooth. And here we just have u going to phi of u, phi1 up to phi n of u. So I'm going to say that u is always going to be for me the variable in the source, at least of the geometrical morphism. And of the target, I'm always going to denote the variables by x. So in here, I recall that if I have a morphism like this, then we have the pullback morphism, right? So the convergent power series in the target, so in x, which can be pulled back to convergent power series in the source. So this is we're going to play between these two, the actual morphism and its pullback, and u is always the source, the geometrical source, and x is always the geometrical target. Okay. Now, the general question that is trying to be asked here is what can we be said about the image of phi? Okay. It's kind of a general question here. And in order to do so, we're going to think about two kind of ranks, which are very common here or very natural to define. So the first one, given a germ like this, is what we are calling the generic rank. So this is the dimension as a topological space, or not a dimension as a topological space, but the generic dimension in terms of its topology in the target. So we look at the image of the morphism, and generically, the rank of the Jacobian is going to be is going to have some minor which is non-zero, and some minor of highest possible rank. And in those points, you're going to have that the image is actually a submanifold of your target. Now, you're going to have singularities. They're going to be special points, so you cannot just define it like that. But essentially, this is the differential dimension of the image. And on the other hand, another thing that we can do is to consider now the image and try to take its Zariski analytic closure. So we take the smallest analytic set which contains its image, and we look at its dimension. So this is just a way to, like the correct way of it, the formal way to define the dimension of the smallest analytic set which contain the image. And in order to keep track, like why are we talking about this kernel here? So the kernel of the pullback are nothing else than the functions in the target, such that when I compose with the morphism, I obtain zero. So of course, these are functions which are zero over the entire image. So this is the ideal that generates this smallest analytic set containing the image. And it follows kind of from usual observations, just about topological observations, that the differential geometry, the differential rank is going to be smaller or equal than an analytic one. You're always going to have that generically the dimension of the image is going to be smaller than the dimension of the smallest analytic set that contains it. Now, just a couple of examples to see what we're talking about. So first of all, the example that has to have in all talks that is going to talk about singularity theory, we have to do the cusp. So if we take the morphism that sends u to u square and u third, then you have the source being the axis here. I'm taking R so that we can make the drawing, and the target, the image is going to be the cusp. Now, the generic dimension of the image as a differential manifold is 1. It's generically a differential manifold of dimension 1, so that is the generic rank. Furthermore, if I take the closure, the Zariski analytic closure of it, I'm going to obtain, I'm going to obtain the cusp itself. So the analytic closure, the analytic dimension is going to also be equal to 1. As a second example, if we take now R2 to R2, and now we have this kind of monomial application that we have here, then we're going to send, let's say, a box like this. I'm taking this box, and I'm going to send it to this kind of figure here. So once again, if I take a generic point, so it's going to be in the middle of this figure here, the differential dimension of it is going to be, or the topological dimension of it is going to be 2. So the generic rank is equal to 2. Moreover, if I take the Zariski analytic closure of this set, then I'm going to obtain everything. It's going to be R2, right? This is the smallest analytic set which contains it. It's R2 itself. So once again, the analytic dimension of it is equal to 2. Now, there are two things about this example that are interesting, right? We're always having the generic and the analytic dimensions are the same, and this is no coincidence. If you go for classical results, so in Chevalier in the general complex case, and Tarski for the real analytic one, for the real algebraic one, sorry. If the map that we're considering is polynomial or algebraic, then the two ranks are always the same. This is an important result. Another result that is quite useful and goes in the same direction is for the case of complex analytic mapping. So if you have a complex analytic spaces, a morphism between complex analytic spaces, we need to ask that the morphism is proper. This is an important thing. And furthermore, the target is reduced. It's just a technical hypothesis. Then the image itself is an analytic space, so you also have some sort of relation between the two ranks, almost everywhere. If X is connected, then you actually have equality everywhere, even in the complex analytic case. Now, in the general analytic case, nevertheless, it's a classical example of Osgood showing that actually this is not true. It's not going to be equal in the general analytic case. So even in the complex case, if the map is not proper, we're not going to have equality. So here's basically the morphism. You send uv to u, uv exponential v, and the crucial point here is that 1 v and v exponential v are three functions which are algebraically independent over c. And because of that, we are able to prove that actually the analytic rank is 3. And kind of the idea is that what is a function in the target which is going to make this phi equals 0, right? So if I wanted to do this, then the function that you're going to choose is something of this order, x3, which is going to be this term, which is going to be equal to, well, let's say the second one, uv, right? This uv that's appearing here. And the exponential of v becomes the exponential of x2 divided by x1. So, okay, this is the function that you would like to define that is going to annihilate the image. But the problem is that f is not analytic itself. It has an essential singularity. You cannot just multiply or play with it. It's not meromorphic. You cannot play with it so to get an analytic function. So you don't have any analytic set of dimension 2 containing the image of this morphism. You're bound to have that the closure of it is going to be the entire K3, or in the entire C3 in this case here. So that's why the analytic rank is bigger. So this leads to a question, okay, the analytic functions they don't behave as the generic topology, as its topological dimension, but there is a very close relation with its formal relation, with formal power series, right? So if I look back into Osgood example, I'm going to see that the same argument would work for formal power series. If I take F here as a formal power series, there's nothing that I can do so that I have the composition is going to be 0. And there's no power series which is not the 0 one, which is going to satisfy this. So this leads to the question of, okay, so what if I define now the formal rank? So I'll define it as essentially the same thing. I want to look at the image and look at the smallest formal germ which contains the image. So the right way to define it is that you take an extension to the completion, you take the pullback, you look at the kernel of all of the formal power series which are 0 over the target, and you look at the dimension of that analytic set, or that formal analytic set. So you can define that as a dimension, and it follows quite immediately that this formal dimension is going to be certainly smaller than or equal than the analytic one. It's much less clear to see this other relation because this is not a true geometrical object. It's essentially a algebraic one, and we're comparing with a geometric condition, but it can be proved. So you do have these inequalities here. And then the question coming from Grothendieck is it true that the formal rank is always equal to the analytic rank? So in some sense, if I find formal power series which are 0 over the image, can I say that they converge? Now, the first thing is that Gabrielov proved that the answer is no. So this is in 71. And he provides a map from C2 to C4. So basically modifying Osgood example, and this was quite, okay, so basically modifying Osgood example, it shows that there exists a map where each one of the ranks are different. So 2, 3, and 4. And this was quite surprising at the time because it was not expected to have this kind of transcendency just with analytic maps. And there you go, you do have it. You do have space for this kind of object to be very transcendental. And furthermore, what I'm calling here a fundamental theorem that he proves is that, okay, that's not possible. We don't have these relations, but there are conditions where we have all of the equalities of the rank. So if I do have that the generic rank is equal to the formal rank, then all of them coincide. And this is an interesting kind of theorem because having the generic one equals to the analytic one means that the morphism that you're working, which is then called regular in the sense of Gabrielov, is a morphism which share good properties with the category of algebraic morphisms. So this is a good thing. And like this is something that is restrictive, restricts the class of the analytic morphisms that you are considering. So it allows you to prove stronger results based on that. And the result provides a just formal condition in order to obtain this kind of result. So just by verifying it formally, you obtain the convergence result. This is normally these are useful kind of results because formally you can always try to verify by manipulating expressions of formal power series, one homogeneous term at a time. So a couple of remarks about this theorem, about the statement of the theorem that I gave here. So the results also hold true for complex analytic morphisms. So between singular spaces, it doesn't have to be, once again, the target should be reduced, but besides that, it's really for any single analytic space. And we can also reduce the real analytic to the complex analytic case just by considering a complexification. So from now on, I'm gonna just assume that, the field is C. Okay, so the original proof of the result was given by Gabrielov in 1973. As I said, the proof is considered to be very difficult. Later in the 90s, Thujeron tried to clarify the difficult part of the proof, but the proof is still considered very difficult. There are some issues with the proof that he provided in the 90s. So it's still not clear enough, especially what we call a difficult part of the proof, more in a bit. And now our result is a new try to our way to interpret their proof and to try to clarify and develop techniques based on Gabrielov and Thujeron's contributions. So their paper, we don't fully understand their paper, but both of their paper are influential to us. And just to give a little bit of motivation about it, there are several applications that are connected works to this kind of result. So general works about study of map germs, you have Viken and Harris, classical kind of paper from 1977, Izumi, the works of Izumi from the late 80s. In foliation theory, there you have works of Lagrange about convergence of first integrals, same for Servo-Mattei. Subanalytic geometry going back to Bierson, Schwartz, and Millman in the early 80s, and especially a lot of works of Pavutsky, interesting works of Pavutsky. And the fact that the map is not regular in the sense of Gabrielov is something that has been exploited in real analytic geometry to provide counterexamples to results that were believed to be true because they hold it in a complex case. So you go back to an example of Pavutsky in 89, which was a counterexample to a conjecture of Hironaka, of Bierson and Paruzinski in the 2020, and of myself and Bierson about global memorization of real analytic morphisms. So you have connected works to this kind of result. Okay, so without further ado, the rest of the talk, I'm going to jump into the proof. I want to try to say what kind of techniques intervene here, what is the difficulty, what do we have to develop. So the first thing is to reduce to what we call the difficult part of the proof, which is actually quite surprisingly the low-dimensional case. And this will follow by a classical approach in irrational geometry, right? Well, here is not birational, but classical approach in algebraic geometry, let's say like that. So given a morphism like this, from CM0 to analytic morphism germ from CN0, where we suppose that the generic rank is at least 2, which is equal to the formal rank, so we are in the hypothesis of Gabrielov, but we are going to suppose by contradiction that the analytic rank is strictly bigger. So you have at least one formal series which does not converge. Then what we're going to produce, and that's the first thing, a low-dimensional morphism, one from C2 to C3, such that the generic rank is equal to the formal rank equal to 2. Typo, this is supposed to be analytic, and the analytic rank is equal to 3. Sorry, this is a typo. So the same kind of statement here, right? The other one can only be 3. The closure of the image has to be C3. And this is the proposition that I'm kind of going to assume. I'm going to treat it qualitatively. How do we pass from the general case to this low-dimensional case, which is going to be actually the hardest part? Proving the low-dimensional case is the hardest part. Passing from the general case to the lowest dimensional case is a part which is quite well understood and was well understood in the proof of Gabrielov already. So the idea is to use certain number of what we're calling allowed operations. So we're going to build this morphism a step at a time. And I want to start by just making a remark about what kind of allowed operations are we able to do. The first remark about this passage is that if I just take a morphism, analytic, and I either make a blowing up, local blowing up, or a power substitution in the source, or if I make a power substitution in the target, so this is the target, Cn, then the composition, the new morphism, will have the same ranks as the previous one. So if we started with one that contradicted Gabrielov's rank theorem, and we make either blowings up and power substitutions in the source or power substitutions in the target, we will not change this contradiction, maintain it. And these are kind of the allowed operations that we're going to use. And there is something interesting here, is that blowing ups in the target, you remark that we are not adding blowing ups in the target because they do change the ranks. And this kind of gives the heuristic about why passing from the general case to the low dimensional one is going to be actually the simple step, because from that point of view, we're actually doing arguments which are purely local, right? We're going to use commutative algebra. And when we do this difficult case, the low dimensional one, we're going to, as we're going to see, we're going to make blowings up in the target. So now the arguments that we're going to have to make are going to be global and not local in nature. So this means that it's going to be a little bit harder. At least heuristically, it already tells us that it's going to be harder. Now, the second remark is about what else are we going to try to, what other kind of results do we need? And we are going to have some sort of decreasing dimension in the structure of the proof that will not work at some point when a certain dimension is reached. So in order to illustrate this, let's just consider a morphism like this, going from Cn to Cn plus 1, where n is bigger than 2. Okay? And we assume that the generic rank is equal to the formal rank equals to n, and the analytic rank is equal to n plus 1. So if I take the closure of the image, I'm going to obtain Cn plus 1. But since the formal rank is equal to n, I do have at least one formal expansion whose composition with phi n is equal to 0. So I take this formal expansion. And I can assume, just by using a formal Weierstrass preparation theorem, that it is actually given of the following form, where we do have one variable here, a y, which is distinguished. So we're seeing this Cn plus 1, so we're going to have x1 to xn, and then you have the one more variable, this is the y. So by Weierstrass preparation, I can distinguish one of these variables, and I can assume that the formal series that is in the kernel of the formal expansion of the formal morphism here, the one that passes to the completion, is going to be generated by this function here, which is just a Weierstrass polynomial in y, which we also can assume to be irreducible. This is kind of a crucial point in here. Now, what we're going to do, if n is bigger than 2, we're going to restrict this morphism to a sufficiently generic hyperplane H. Let's not be too clear about this. We don't need to be entered the details, but we restrict it to a sufficiently generic hyperplane in the target. We look at this spray image. Under allowed operations, we can show that this spray image is actually equal to isomorphic to Cn minus 1. So we're going to obtain a morphism just as before, from Cn minus 1 to Cn now, because we restrict it to hypersection, where the generic rank is going to be n minus 1. And the formal expression that is here is also going to be a restriction over H. So it is also going to be there. So we still have a divergent series there. So the formal rank is still n minus 1. And we have to argue that the analytic rank does not go down. It does not go to n minus 1. It stays as high as possible. It stays equals to n. And this is the passage that I want to make a remark about. How do we do that? We do that by using two theorems. One of Abiancamo from the 70s, which says that if I take a polynomial which is divergent and I restrict to a generic, a sufficiently generic hyperplane section, then the restriction is divergent. So that's a good thing. This indicating that analytic rank is not going to drop. But we need a little bit more. We need a result that is only true for n bigger or equal to 3, which is some sort of formal Bertini theorem, which states that if I take a polynomial like that, which is reducible, and when I restrict to it, it's still irreducible. So this kind of theorem is not true if n is equal to 2. This is a very simple counterexample, right? If I take x2 equals to 0, then this is a polynomial that factors into y minus x1 times I plus x1. Very simple. So it's not true if n is equal to 2. And therefore, if n is equal to 2, what could happen is that when I restrict that formal polynomial, which is still going to be formal according to Abiancamo, it can factor now into two parts. And each one of these factors here, while one of them might be divergent, the other might just as well be convergent. And if one of them is convergent, then the analytic rank would drop to n minus 1. So this statement here is only true if n is bigger than 2. So that is why the case n equals to 2 is going to be the hardest one. So here is the low dimensional rank as stated as before. So the case of n equals to 2. So the source has going from C2 to C3. And we're going to assume that the generic rank is equal to the formal rank is equal to 2. And what we want to prove is that the analytic rank is equal to 2. This is our goal. And now we're not doing this by contradiction anymore. we're just going to suppose that we are in this condition. So by formal Weisser's preparation, once again, we can distinguish a variable, as I said. We're going to have x1, x2, y, and the generator of the kernel of the formal extension is going to be an irreducible polynomial. So it's kind of important in the beginning to have the word irreducible here, so that we keep track of what is the difficulty of the form as before. But now AI is just a coefficient in Cx1, x2, and our goal is to prove that this polynomial is actually convergent. So our goal is to show that it's actually convergent, and therefore we do have an analytic set of dimension 2 containing the image. That's our goal. So as I said from remark 1, we're going to have to change our kind of framework. We're going to have to spend now time not doing commutative algebra, but actually doing geometry. So it's convenient to change the notation to a geometrical notation. Here is the points that we're going to take, a C2 point. I will denote by OA the ring of formal power series at the point A of the germs analytic functions at A. And P for us now is just going to be a polynomial which has formal coefficients in respect to the point in the germs at A, which is a polynomial in Y. Now, given a finite sequence of blowings up in terms of x1, x2, that's kind of the transforms that we're going to do. So some sort of blowings up here. F is going to be the strict transform, the exceptional divisor of the sequence of blowings up. So it's the preimage of the point. And given any point B in F, so in the preimage of sigma 1, sigma of A, we can consider the pullback of P by sigma at the point B. That means what? That means that I will take just P, and I will look at the coefficients, and the coefficients I'm going to compose with sigma, at least formally, right? We can do this always in a very nice way formally. Now note that all of the transformations we're going to do are going to be invariable by this variable y. We're not going to touch this variable y. Okay, all the transforms are only going to change the coefficients of P. And the detail here is that even though if P is irreducible in the beginning, the pullback may not be reducible. So this is linked with the second remark that we made, and it's completely linked to that. So this is kind of the point, and something that we have to take care little by little in the proof, which motivates us to look at what I'm going to call the convergent factors. So given a polynomial as before, a priori just divergent, and instead of irreducible, I'm going to demand it to be reduced, because this is a property that is preserved by blowings up in terms of the coefficients. Monic non-constant polynomial, we will say that P admits a convergent factor if it can be factored out in two factors, non-trivial factors, or trivial. The R can be trivial, sorry, but the important thing is that this Q should be convergent, and it should not be trivial. So of course, if P is irreducible and admits a convergent factor, then P is convergent. So the goal is to show that that original P actually admits a convergent factor. From the fact that it's reducible, we conclude that it's actually convergent. Now, what is the base of our induction procedure here? It's going to be an induction in terms of the blowings up. Well, first of all, if the degree of P is equal to 1, then P is convergent. And this follows just by computation in terms of the morphism. We know that the morphism writes as y plus a0 of x1, x2. And if I just compose with the morphism, I will have that this analytic, you have a formal series composed with two analytic entries. And you can show, just using the complex analysis, basic complex analysis, that A itself, A0 itself is convergent, and therefore P is convergent. Now, if you suppose the more general interesting case that the discriminant of P is monomial, that is, the discriminant of P is of this form, then we have the classical Bianca-Young theorem that we can use, and that will describe us in a lot of details how are the roots of the polynomial P. So we can write P as a product of coefficients, of very nice coefficients, y minus these CIs, which are all formal power series, and apart from our ramification, we're factoring to terms of degree 1. So this is kind of the idea here. So up to a power substitution, we can assume that this k is equal to 1. So in this case, P would factor out in a lot of terms of degree 1. And if you're in the case the k equals to 1, then by the first case here, sorry, I did not change this part, at least one of the CIs is convergent. And then you can come back just by using a little bit of commutative algebra and say that the original P itself, before the ramifications, it already admitted a convergent factor itself. So this is the case that we're kind of aiming for. So how are we planning to do so? We're planning to do so via some sort of inductive framework that will depend on a number of blowings up. So we're going to start with this polynomial that we want to show that it's convergent. And what we're going to do is that we're going to do a sequence of blowings up of points up until the moment that the pullback of the discriminant of P is monomial everywhere. So the discriminant of P is a formal curve. Now, a formal curve admits resolution of singularities via blowings up of formal points, but fortunately, formal points are convergent points, so everything here is analytic. You do have the sequence. It exists. And for this induction scheme, it's going to be useful to keep track of the history. So FR1 denotes the strict transform of the first blowing up, and so forth. So FRR is just the last exceptional divisor there up here. Okay. So this is our overarching framework. This is what I'm going to follow for the rest of the talk. We started with just this polynomial here, which is formal. We're bringing it up to our inductive base step. So the case that we can use a Bianca-Young. We use resolution of singularities to show that discriminant is now monomial. This is the framework that we're going to use. Okay, so the first proposition that is going to give us now the result, and that is going to, it's the last slide that I'm going to use actually, the morphism, is that under this framework, I will assume that there exists a C in a FR such that the polynomial, the pullback of the formal expression in C has a convergent factor. And what I'm going to show is that P admits a convergence factor. So you see that there's as it's going to appear in the statement of the proposition, there is no assumption over phi. And how do we prove the low dimensional Gabrielov from here? So what we need is just to prove that this hypothesis is verified. There exists C in FR such that PC has a convergent factor. This is what we need to prove in order to use a proposition and finish, show that P converts. So we start with this, with the morphism. I'm forgetting the variable y here. And I make the overall sequence of blowings up. So this is the overarching framework that we're talking about. Now, since these are blowing ups, I can always take complete the diagram via blowings up in the source, so that I actually have a commutative diagram like this, and I actually have an analytic morphism going out from some LD here, L, the variety that is sent to C2, and D is the exceptional divisor of the sequence tau. And now I have this analytic morphism. So there's at least one point of D which is going to be sent to a point of F. So this is our C. And over that point C, I now have the condition that over this point, it is in the quasi-ordinary case, because that's the assumption that we made for sigma. Now the pullback of P is everywhere, has everywhere the discriminant, which is monomial. So we can use the base case, and therefore we are in the conditions of the proposition. We can assume that there exists a C in FR somewhere, such that the PC has a convergent factor, and therefore the regional P is convergent, as we wanted to prove. Now, I'm not going to talk too much about how to prove this proposition in terms of the induction, but I want to talk about the main technical point in it. And the main technical point to prove that proposition, and from now on, we do not need anymore to talk about the morphism. We just need to keep track of the notion of convergent factors, is the following. Under the framework, if we assume that the point C, where the polynomial PC has a convergent factor, let us assume that it appears in the first blowing up. So it is in the exceptional part of coming already from the first one. And let's suppose that it does admit a convergent factor. Then what we want to prove is that there exists some open set, actually, over the entire divisor, the first one, and a polynomial defined over there, such that this Q is a convergent factor of P along the entire divisor. So this is something like, from something which is defined only locally in C, we want to extend it through the entire divisor. That's kind of the idea that we have here for this main technical tool. So I'm not going to tell you how to pass from the main technical tool to the proof of the induction scheme, I'm going to notice that if we only had one blowing up, then this kind of result would already kind of imply almost directly that you would be able to prove the proposition there. But I'm not going to talk too much more about it, just essentially because of time constraint. And what I'm going to do is to jump into the proof of this proposition, the semi-global extension, which is the most difficult part. Now, just to recall, we wanted to prove Gabrielov rank theorem. We said that it was enough to prove the low-dimensional case. We said that it was this inductive scheme and the quasi-ordinary case that would imply it. And we are with this proposition, which is the semi-global extension. Now, the proof of the semi-global extension, it will have two steps. And the techniques are inspired by the work of Tougeron. So here we deviate from the approach of Gabrielov. We got inspired by Tougeron himself. We're going to have this kind of two tools, some sort of Newton-Puiseau parametrization, and the passage from algebra to geometry, which we are calling local to semi-global convergence of vectors. Let me just keep track of the time. Yes. Okay. So let me jump into the idea to prove that semi-global extension result. So what are we searching? Okay, we search a subring R of the algebraic closure of Cx, which will have a very important property for us. So it has to be big enough so to capture factors of P after one blowing up, and factors which are defined over the entire divisor. So we can think of the following form, like when you have the polynomial P, which is irreducible, it's a formal polynomial which is irreducible, you blow it up, then at every point you may factor. But you also may look at the factors which are globally defined over the divisor, right? So you might have that the factorization happens over the entire divisor. You actually have factors which are valid over the entire, which are well-defined in formal power series over the entire divisors. So what we want to capture is this ring R, right? So it has to be big enough to capture these factors, right? So we cannot just use the usual ring. The usual ring would be too small because it was a priori irreducible. When we blow up, it keeps to be irreducible. It's not going to capture these global factors. And in on the other hand, we want it to be small enough so that we can manipulate, constrain its elements. So if I just take the algebraic closure, of course, if I take the algebraic closure, then I will be able to write it like this, and I'm going to capture all of these global factors, but I'm not going to be able to manipulate them. They're going to be way too general. There's not going to be enough constraints for us. So kind of the game here is to try to find this subring. So the first thing to do is to try to provide an idea of what the subring is. So at this point, we look at valuation. So it's a natural place to start looking where this ring is going to be. We look at just the usual valuation, the exotic valuation, so just the order, if one prefer. And we consider the valuation ring associated to it. So it's just basically the division F divided by G, where F and G are formal power series. And the only thing that we are assuming is that the order of F is bigger or equal to the order of G. And there's a really good reason to choose that, and it's like you can see geometrically already, because if I do one blowing up, so if I do one blowing up like this, UV, that goes to UV, then the element that I'm taking here, when I pull it back, I'm going to pull back to the strict transform of F, the strict transform of G, and to the power of the exceptional divisor to the order F and to the order G. So since I'm taking order of F bigger than the order of G, this is just U to some positive power. So as long as I'm not in the strict transform of G equals 0, this curve, then I'm sure defining a true element of formal power series. So if I blow it up and I'm not in the strict transform of G equals 0, then I have a true element of formal power series after the blowing up. It's a natural kind of ring to look at it. The other kind of element that we need to keep track of is that we will need to use roots in some way. So if I just take this kind of polynomial here, then I need to add this kind of root. I need to add square roots of some sort. And I want to keep track of them as best as I can. So I don't want to have it in terms of just an algebraic closure and resolving some polynomial. I want to keep really tight track of what are these elements here, which I'm joining with roots. So we're going to call this an integral homogeneous element, some element gamma like this, which satisfies a relation, a nice relation where this polynomial is weighted homogeneous. So the word homogeneous here is important. This is quite constraining. It's going to be weighted because, just as we're showing in this case here, that the polynomial that makes it 0 is of the form, well, 2 in one of the variables and 3 in the other 2. So you can have weights, different weights for each one of the entries, but they are homogeneous in some sense here. And this is going to be the constraint that we're kind of searching for these elements. Now, the projective rings, the candidate for the rings which we're searching, is going to be in terms of these valuation rings. So we're going to look at this homogeneous elements, an homogeneous polynomial, whichever, h. And this h is going to play the role of that g of the valuation. So I said that when I divide by g, I'm going to be well-defined after one blowing up everywhere outside the strict transform of g equals 0. So I want to do this in a way that I'm well-defined, like I want to have one single possible denominator throughout this projective ring, this candidate. So we're going to call it projective ring, and it's going to appear the h that is appearing here, and it is the part which we're going to divide. It has any kind of order. It's going to appear any kind of linear order here in terms of this of the Taylor. No, it's not a Taylor expansion. In terms of some asymptotic expansion here defined. That we can do it in the ring. And the other part is going to be this gamma, which is an integral homogeneous element. So one thing at a time. First, the projective ring with this h. We're going to have the denominators in terms of this h, and the AKs are just going to be homogeneous polynomials of some kind, satisfying the relation between the valuation. So we have that the valuation of AK minus the valuation of the denominator is going to be of order k. So this means that if I blow up, I will have u to the power k times something, and this something is going to be a power series, a real power series, like something well-defined everywhere outside of the strict transform of h equals 0. And if I want to go further and really describe things, I'm going to add these homogeneous elements. So I'm going to add some integral homogeneous element. And in that case, I'm going to have this kind of expression here, where the coefficients are basically in the previous ring, and these gammas are these homogeneous elements that we are adding here. So this is how we're going to describe all of the roots which are possible. Now, the first result, which established some algebraic relation between, so it tells us that the ring that we're searching actually gives us at least algebraically what we're searching for. It's not yet geometrical, but algebraically what we're searching of is what we're calling the Newton-Poisson-Einstein factorization. So starting with this polynomial, any monic polynomial, it doesn't have to be irreducible, it doesn't have to be reduced. There exists an integral homogeneous element, so existence of homogeneous polynomial, such that we can factor into the QIs, where these QIs, they belong to the pH of X. So these are going to be our irreducible terms in the valuation ring. And therefore, since they are in this projective ring in H, it already it satisfies generically what we were searching for, right? If we make the blowing up, then P is going to factor in terms of this QIs, in terms of the blow up of this QIs, everywhere outside the strict transform of H. So we're going to the right direction, right? We're not yet capturing entire exceptional divisor, but almost all points of the exceptional divisor. And furthermore, there exists this homogeneous element such that when I take each one of these QIs, I can factor into degree 1 polynomials, where the Cij's, they do belong to the ring that we are looking for. And again, one important thing, these gammas, they are zeros of weighted homogeneous polynomial, and this is going to be important for us later on. Okay. Now that we have this kind of formal algebraic setting, we want to pass it to a geometrical setting. So what we're going to look at now is some sort of start defining what is going to be a geometrical setting, so a convergence setting. So we're going to look at some subring of that general ring pH, projective ring. We're going to look at the subring of convergent power series in some sense. So this is going to be denoted by pH with the brackets here, X. So it's characterized by the following. If I take an element, so an element of the previous ring, it was given by this kind of formal expansion, right? We have some homogeneous terms ak divided by some powers of that homogeneous polynomial h. And what we want is that if we ignore the h, then it's a convergent. Then it's a convergent term. And if you have this, if you just assume this definition, like why I'm saying assume, because we have to prove that this definition is well-defined. I'm going to make a remark about this in just a second, but let's just say that for now that it's well-defined. If you just look at this intuitively, then what is going to happen? When I blow up, the formal expansion of A is defined everywhere outside of the strict transform H equals 0, and possibly of other exceptional divisors, because other exceptional divisors might contain an H equals 0 coming somewhere here. So almost everywhere outside of the strict transform, everywhere outside of the strict transform of H, you will have that the formal expansion, that the pullback of A is going to be well-defined at that point. Moreover, I will have that the numerators are going to be convergent. So what we're going to have is that it's going to converge at some point here, some neighborhood. So you'll have that terms like this, when you pull back, they will be convergent along, it's not an open, along an open set. It's an open set. It's not a neighborhood, it's an open set. Open sets like this, which degenerate at H equals 0 or possible other exceptional divisors. But along everywhere else, it is convergent. So it's kind of doing, it's starting to do the job that we want. It's starting to capture these global factors. The remark is that it's not trivial to prove that this definition is well-defined. It's actually kind of tricky, kind of subtle. We do need to use complex analysis, and essentially it's because this, like for an element of the ring, there are many possible ways to describe it. There are many possible sums that we can make out of it. It's not unique, the way to represent it. Now, the next step is some sort of local to projective convergence of factors. So what it means, like we do have a factor defined over a point C. And what we want now is from a little point C and defined over locally, we want to pass to some factor defined over at least an open set as the one that is written here. So we want to prove the following result. So suppose that there exists a point C such that the polynomial emits a convergent factor. Then what we want to show is that there exists one of these qi0 here, one of the terms, one of these factors in the projective rings, which is actually convergent. And the difficulties I'm trying to capture is that when I localize at the point C, then this term qi, it might factor out. And the only thing I know is that one of these RAJs is convergent. We have to prove that all of them are convergent, right? So we only have information over a little open set, and we have to have some information over this global neighborhoods. And the key point here is that the qi belongs to this nice ring where the gamma is very constrained. It's all linked by this weighted homogeneous element. So it has this weighted homogeneous polynomial that is 0 of it. So you are able to do global arguments and pass from one root to the other. So this is kind of the key point here. And then we are able to prove, we actually follow an argument of Izumi from the 90s, that we learned with Izumi from the 90s. And finally, the last point is, what do we do with those points h equals to 0, right? So in here, we are going to use the fact that if these qi's are coming from a polynomial, a true polynomial, because this is a formal polynomial, so when I blow it up, even at the points where you have the strict transform of h equals 0, you're going to have a true formal expansion, right? A true formal power series. So the product of all of the QIs, even if you do not know what could be defined at h equals to 0, the product of them is a true formal expansion power series. So in this case, under this kind of hypothesis, we can actually show that the QI extend formally at every one of the points. So extend formally is exactly what we think it is. So it means that when I take the pullback at that point, it does belong to the formal ring. I don't have poles of any order. I just have an extension. And furthermore, if A extends analytic at B, and if QI is in the convergent projective rings, then the extension is also analytic, so it's even more the pullback is analytic. So this is what we wanted. And two remarks about this. The first one is that the theorem is not trivial, even in the case that the P is an analytic polynomial. And why is that? Because this theorem basically shows that the projective ring that we're searching has the property that we wanted. It's going to capture all of these global factors along the entire divisor, at least under the framework that are all under certain conditions. So it's not trivial even in the analytic case. Now, in the analytic case, we can prove it in a very simple way, just by using a Bianca-Young theorem once again, because this is part of the assumption that the discriminant is normal crossings over the divisor, and by using analytic continuation, right? We can, from this kind of setting here, we can use analytic continuation to show that you can extend it to this point. Now, the case of the formal, you cannot do that. There's no analytic continuation. You still have a Bianca-Young, but you don't have formal analytic continuation. So we have to replace it with some other kind of argument. And what we use is then Artin approximation theorem. So we approximate the polynomial by convenient analytic ones, and then we show that the factors have to converge too. So by using the analytic case with this analytic continuation, we provide a proof for the formal case via Artin approximation, via a formal approximation kind of result. And with this result, we have extended all over the point, so we have been able to recover the semi-global extension as we wanted. This is the kind of technique that we were searching for. Thanks a lot for your attention. Here I finish.
Thank you. Thank you very much, André, for such a nice talk and a very interesting result. So now we have time for questions and remarks. Please post them in the chat, please. Well, meanwhile, let me ask you, I have two questions, in fact, but let me ask you the first one is the hypothesis of the Gabrielov theorem a topological invariant? I mean, if the two mappings, phi1 and phi2, formal or analytic, if one map satisfies any other topological equivalent to it, also satisfies?
So I don't believe so, but I don't think that the formal one is going to be topological. But.
Well, I think in the real case, maybe it's not so hard to see that this is not true. But in the complex case, I think it's a question. I mean,
okay. Then is it a topological invariant? Okay. Then I don't know. I haven't thought about it. Honestly, I haven't thought about how to.
Okay.
What was the?
So.
Also, there's a question.
We have another question from Felipe Monteiro. Is there a geometric meaning for the pullback theorem, remark 2 of the general case, not holding for n equals 2?
For n equals 2. Is there a geometric meaning? Yes. So, well, the theorem does hold, right? You mean the Scholl's theorem, right? I think that might mean Scholl's theorem. Is it? Is this the theorem that you're thinking about? The formal Bertini theorem of Scholl? No?
Yes.
Okay. So yes, the intuition here is that if I take any generic hyperplane section, if the n is bigger than that, then I can actually see this result much more in an algebraic sense. If you make cuts in terms of hyperplanes, you're not gonna being irreducible is something that you're not gonna capture if n is big enough with hyperplane sections. And for n equals to 2, you have very simple counterexamples like this one, just because you only have one direction to vary, right? It's kind of the idea here. You only have one projective direction. I do not know if that answered the question because I'm not really sure I understood the question. Or if there's another remark from Rafaela.
No.
Okay.
Let's wait a second. Any other question? Okay. So let me go back to my question, kind of related to what I asked. So it's not difficult to see that the hypothesis of the theorem holds in general, both in the formal set or in the analytic sense, right? In the sense that most maps satisfy the condition, right? And we see this, for instance, from the fact that it holds for polynomial mappings.
Right.
And, at least from C2 to C3, we know that it holds in general that mappings, analytic mappings, are equivalent to polynomials, right?
I see. Then
even analytic equivalent to polynomials. But this is true from C2 to C3, it's not true in any dimensions.
But equivalent, okay. Yeah.
Equivalent by changes of coordinates in source and target, right? From C2 to C3, this is true.
But for example, Osgood mapping, how do...
It holds in general most maps. So most maps. So the set of maps.
Most maps. Sorry. Yeah. Okay.
Maps
yeah. Then I agree.
Does not satisfy this condition. Is a very small set in the sense that its codimension goes to infinity, right? So, but of course, from your talk that it's not true that this is that the hypothesis of the theorem implies that the map is analytically equivalent to a polynomial, right? But anyway, since it holds in general, since this condition holds in general, it's very interesting question to know what class of mappings, what properties of mappings satisfy the conditions of the theorem, right?
So, I see. Nice. So what kind of hypothesis we could add? Just we have an analytic map. What kind of hypothesis could we add a priori so that... okay. And is there a class that you think that it would be interesting to study in particular?
Well, there are conditions that guarantee, that's why I asked whether it's a topological invariant, because if you think about change of coordinates that are homeomorphisms, then you are talking about a larger class, right?
See, I've been looking at this question in a different sense. I've been looking at what about classes of functions which contain the analytic functions? Is this theorem still true? So I was looking into that kind of direction. So it's true that this other kind of question, which is now what kind of subclass of analytic functions can we obtain this kind of hypothesis directly? This is something that I didn't think about.
Yeah.
Well, maybe. Okay.
Very
interesting to look.
More questions? So thank you very much for your nice talk. Thank you.
Thanks a lot, Cidinha. Thanks for everyone. Thanks for the organizers.
The next talk will be in 10 minutes. Thank you.
Good morning, everybody. It's my pleasure to introduce Marcelo Escudeiro Hernandes from Universidade Estadual de Maringá, who will talk about the analytic classification of plane curves. This is the last step toward the solution of Zariski's problem stated in the 60s of last century. Please, Marcelo.
Thank you, Abraham, for the introduction. And thank you, the organizer, for the opportunity to talk about this joint work with Maria Helenice Rodrigues Hernandes. Let me see. Okay. And I'd like to congratulate the organizer on the excellent and non-trivial organization of this international workshop, singularly in this special edition. So, it's okay with my slide? It's okay,
Marcelo, yes.
Okay, thank you, Abraham. Okay, well, in this talk, by a plane curve, we mean a germ of a singular plane curve given by a zero set of a reducible element in the maximal ideal of the convergent power series rings. We denote by Ci a branch associated to the reducible factor of F. And in this talk, we will present an answer to the analytic classification problem in a fixed topological class. Let me recall this equivalent relation. We say the curve CF is topological equivalent to CG, if and only if there exists a homeomorphism and neighborhood V and U at the orange, so the image of V, the intersection of V and CF, is the intersection of U and CG. When the homeomorphism is also an analytic isomorphism, then we say the curve CF is analytical to the curve CG. Many authors has been considered this problem to the analytic classification problem. For instance, in 1965, eBay classified particular topological class for irreducible curves. In a famous course in École Polytechnique, Zariski extended this classification and consider also the moduli problem, the problem to describe the moduli space and compute its dimension. Bruce and Gaffney classify all the simple germ in the reducible case. Luengo and Pfister, and Landau and Pfister classify particular topological class fixing analytic invariant, the Chirinas number. Koguskin and Sadikov classify all simple germ for reducible curve. Kang, Kamara, and Scardo consider the quasi-homogeneous case. And in 2011, in a joint work with Abraham Hefes, we solved the analytic classification problem for the irreducible case. In 2015, in a joint work with Hefes and Rodrigues Hernandes, we solved this problem, consider the B-germ case. Our approach following the ideas of Zariski, that means we consider parameterization and we fix a topological class and consider some analytic invariant, we stratify the moduli space in order to obtain particular representative, the normal forms or the short parameterization, as Zariski called this formula, in order to distinguish two plane curves up to the analytic equivalence. So let me recall some aspects relative to the parameterization. Consider a reducible curve, Ci is a branch, with multiplicity Ni. We can parameterize it by a pair of our series in Ct, where the order of one of the components is equal to Ni, and the order of the other component is equal or bigger to the Ni. We identify such parameterization with the smooth metric germ for C to C2, and for a curve with several branches, we associate a multi-germ given by this matrix, and in each column, we put the parameterization associated to the component of C. And P means the set of all multi-germ of plane curve with R branches. The next step is put the curve in a convenient position. In order to do this, we translate the analytic equivalence to the action of the direct product of the symmetric group on R element in the classical A group. The action of the A group is classical, and an element in A acts in a multi-germ in this way, where we have independently chain of parameters here, but we have the same chain of coordinates sigma 1 and sigma 2 are the components of the sigma, and the symmetric group acts on the matrix in this way, in the multi-germ in this way, just by permutation the elements, the columns in this matrix. So, it's a very well fact. If you consider 3 distant lines, we can move by change of coordinates in other 3 lines. So, in this way, we moved our curve in a convenient way, and we chose the tangent line with slope 0, infinite, and 1. Of course, if we have three tangent line distance, okay? So by A equivalence action, we can adjust the multi-germ in a particular way we call a block form. So given a multi-germ in P, we group their components in blocks in such a way in any element belong to the same block has the same tangent. If you have just one block, the tangent has a slope equal to 0. If you have just 2 blocks, we shows the tangent line here with slope 0, here infinity. If you have 3 or more blocks, the third one, we shows the tangent slope equal to 1. And we order the elements in the same block according to the multiplicity, and we order the blocks according to the minimal multiplicity of their element. So this is why we call a block form. So in order to maintain the block form, we consider particular subgroups of the A group. So we consider the classical A1 group, that means the one jet is equal to the identity. The A1 tilde differs of the A1 group because we consider the one jet of sigma given in this way. We have an extra term here. Age denotes the homothety given by this, and H prime denotes a subgroup of homotheties when we consider alpha and delta equal. So consider this subgroup of A, in order to preserve the block form, we have the following subgroup of A according to the number of tangents, distant tangents, or blocks. If we have only one block, so any element in A that preserve the block form can be rewrite using an element in A1 tilde and an element in H. If you have just two blocks, so the element is split in element in A1 and element in A. If you have three or more blocks, then the group A1 and the group A prime play the game. Okay? So the group H, the homotety group, doesn't introduce or remove terms in a parameterization, in a multi-term. So in order to obtain a short parameterization or a normal form, it's convenient to consider the group A1 and or A1 prime according to the number of block. And a tool to this task is the complete transversal theorem given by Bruce, Kirk, and Duplessis. Here is a concise form for this theorem, and we recall if we have G, a Lie group, acting in a affine subspace, we respect a vector space V, and W is a subspace of V, such that the tangent space of the orbiting of all element in the affine space is equal to the tangent space to the orbit of V plus any element in W. So, under the hypothesis of the W is a subspace of the tangent space of order of V, then V is G equivalent to G plus W. So, we can choose W in a convenient way in order to obtain a short parameterization or a normal form. It's a classical theorem in the classification problem. Okay? In our case, if we denote by G, A1 or A1 tilde, according to the number of blocks, so taking the K-jet of G, this Lie group, the K-jet of the multi-terms B, and the C vector space HK, and HK is the K homogeneous element in this way, with an extra condition, the coefficients Ci and Di are equal to 0 if K is less or equal to the multiplicity of the corresponding branches. Then we have this condition, this equality to the tangent space to the orbits for any element in HK. So for any subset in this intersection, we have the hypothesis of the complete transversal theorem. So the idea is describe subspace in this intersection in order to apply the complete transversal theorem. And in order to do this, we consider some A invariants. And the first one we introduce using the evaluation, but before this, we can identify such elements belong to this intersection. In fact, all homogeneous elements in this way, where the star represents a homogeneous element of degree K, and the second block, we put 0 in the disposition, and then other blocks, we have 0 here in this position. Any element in this form belong to the tangent space to the orbit. So, using this characterization or this property, we can recover the Puiseux form, the Puiseux parameterization. In fact, an element in P is J equivalent. J is A1 or A1 prime, according to the number of the block. So any element in P is J equivalent to a block form given by psi, and the components of psi satisfies this one. For the components in the second block, we obtain a monomial element in the second coordinate, and the other blocks, we can consider monomial element in the first one. And here, theta m denotes the slope of the tangent line. So for the first block, theta m is 0, and the third block, if there exists, of course, theta 3 is equal to 1. Okay? So if we have this element belong to this intersection, now we have to analyze the complementary. What can we say about the element given in this way? When we consider the K homogeneous element given by this form, when we have 0 in the first position for the blocks, except to the second one, when we consider 0 here. We denote this intersection, this subspace, by dk. So the idea is try to identify this subspace with some elements, or try to recognize when an element belongs to the dk using discrete invariant. And the first one, A invariant, we introduce is related to the topological classification. And let me consider first the irreducible case. Given a parameterization of a reducible plane curve given by xi and yi, so we can identify the local ring, this quotient ring, with a subalgebra of the power series in one variable. And Qi denotes the field of fraction of Ci. So we can consider the natural discrete valuation, the normalized valuation associated to this integral closure, and we denote by this one, and we can compute the order of any element in the field of fraction. So we denote by gamma I the order of elements in OI, or in more general, if we consider a power series, we can consider the canonical image in OI, and we take the order. This is equivalent to compute the pullback of a power series by a parameterization phi. If we don't consider here the infinitive, we have the classical Simon group associated to the branch Ci, and the Simon group is an A invariant, and it is a complete topological invariant for branches. But we can extend this notion for curve with several branches. And if you consider an element NP, a mu germ, so we define gamma as a R-apple when we consider the valuation of the same power series with respect its branches. So this is a subset of this direct problem, direct product, and this intersection, gamma, this intersection corresponds to the classical semigroup considered by Garcia and Bayer for two branches, and considered by Valdi and Delgado for n branches. This set is a topological, a complete topological invariant up to permutation, okay? And in general, gamma is not a finite generated Simon group, okay? But if we equip this set with the tropical operation considered by the infimo, the addition. So this set is a finitely generated semi-ring. This is a result in this paper in a joint work with Emilio Carvalho. And this is ruled for, not for n plane curve, but for n algebraic curve. And the main advantage is we have a finite element to express any element of the semi-ring. So it's a nice property when you use a finite system of generators. For instance, I think we have an example here. If we consider a mood-germ, so its component is given by this Puiseux parameterization, n and m are coprimes, n is less than m, and the coefficient ai satisfy this relation, then the semi-ring is generated by this element. These are Apple, this one, and are elements given in this way. Notice that the m times m is precisely the intersection multiplicity of two branches. Here is a picture for the case r equal to 3. We have three branches in this situation, and this is part of the semi-ring. When you consider n equal to 2 and m equal to 3. Okay, we will return to this topological class in the end of this talk. Another important thing about the semi-ring or the semi group is the value semi-ring admits a conductor kappa. This means if we shift the nr by kappa, we obtain a subset of the semi-ring, and kappa minus any element in the canonical base of R doesn't belong to the semi-group. The components, the coordinates of kappa is given by the Milnor number of the branch Ci and the sum of the intersection multiplicity of the branch Ci with the other branches. So using this topological information, the kappa and the semi-ring, we can obtain this result. N mood-germ is J equivalent. We recall J is A or A1 prime to a mood-germ given by a polynomial, where the degree of the polynomial in each component satisfies the following relation. Di is kappa I plus 2 if we have just one component, the reducible case, and the multiplicity is less or equal to 2. Di is kappa I plus 1 if we have two blocks and two curves, and the multiplicity is equal to 1. That is the curve, we have two transversal curves. And Di is kappa I in another case. So using only the topological information, we can obtain this proposition. Okay, but in order to obtain a normal form or a short parameterization, we need more information, analytic invariant, and we introduce another invariant, A invariant, using the differential forms. So given a mood-germ phi, we denote the module of one forms given by eta 2 dx minus eta 1 dx, where eta 2 belong to the maximal ideal square, and eta 1 belong to the maximal ideal square in the case of A1 group, and eta 1 belong to the ideal generated by x squared and y if we consider the A1 tilde group. So using this differential form, we get a fraction ideal of the local ring given by this way. We consider a form, a differential form in the corresponding modules, and we take the pullback with respect to the parameterization, and we divide by the multiplicity times ty to the multiplicity. So this is a fraction idea, and depends, of course, according to the J group. And as Ig is a fractional idea, we can compute their evaluation. And the value of elements in AI we denote by lambda j. And lambda j is an A invariant associated to the multi-germ phi. And when you fix a Simon ring, there is only a finite man possibly a number of finite j associated to this. So in the topological class, we can stratify the analytic class using the invariant lambda. And we can compute the lambda j in all case when you fix a topological class using an algorithm, and we represent in this paper in a joint work with Emilio Carvalho also. But I think is relevant to make some remarks. Many authors have been considered a fraction idea associated to differential forms. For instance, Poe, Guzman, and Heffes obtains several interesting properties about the symmetry, about the set of values. And in a joint work with Bayer, Guzman, Heffes, we obtain a relation about a relation between the Turin's number and the Turin's number of each irreducible component. The intersection multiplicity is some numerical invariant associated to the evaluation associate the Kähler differential form. And this is wrote for a complete intersection curve, not only for curve in this result. Another important notion associated to the A invariant lambda is the fiber. And given a subset of index J, the J fiber of an element in a diagonal is given by the elements in lambda J such the coordinate delta J coincide with lambda for every J belong to the set J, and the coordinate delta I is greater than lambda to the others. The index doesn't belong to the J. To illustrate this notion, here we have picture for three branches. If you consider J equal to the set 1, 2, 3, and the J fiber is non-empty, so in this case, the fiber consists just a single point, is precisely the point in the diagonal. If you consider the set J equal to 1, 2, so the fiber is the element in this red line, and that belong to the lambda G. And if J is the set given by just the number 1, so the fiber is all the elements in this quadrant that belong to the lambda J. So using this notion of fiber and the set lambda J and the fraction ideal associated to some differential forms, we can rewrite the condition for an element belong to dk in the orbit and to the tangent space to the orbit. More precisely, there exists a d-dimension subspace in this intersection if and only if there exists a subset of index L such for any element in L, we can associate a set such the fiber with respect to the set is non-empty to the K, and the M doesn't belong to the other subset. Okay, this is equivalent to guarantee the existence of an element in the fraction ideal. So for n choose of complex number, we can obtain an element in the fraction ideal. So the k-jet of the element in the position given by L is precisely this one. It is nice because here we can translate a condition to obtain an element, a subspace in this intersection, in terms of a combinatorial condition. So, as we can compute by an algorithm the set lambda, we can describe the fibers. So, it's possible to identify if we have the star condition or not. As a corollary, if we can K a positive number, and phi is a mood germ, and L a subset of index satisfy the star condition, then there exists a mood germ J equivalent to phi, such the K minus 1 jet coincide, and we can eliminate the term to the Q for all components indexed by the set L. So we have a eliminate criterion using, for instance, the star condition. So, of course, the aim is eliminate terms of order, a fixed order, K, from the greater number of branches, prioritizing the first one, okay? So, we will denote by LK the corresponding set L satisfying the star condition with this property, okay? So, using this notation, we're able to present the J normal form. So, it's the normal form with respect the A1 or A1 tilde group. So, n mood germ phi with a fixed Simon ring and set lambda is J equivalent to another mood germ given by a Puiseux block in this way, such the element T to J can be eliminated in this expression if the index of the branch belong to Lj. Okay, so we have this condition is a consequence. Is a consequence for the previous result, but we have an extra condition. If we have two mood germ psi and psi prime in this Puiseux block satisfying this condition, then phi and psi prime are J equivalent even if they are equal. So that means the J normal form or for a fixed mood germ is unique. So in order to obtain the analytic classification, the next step is consider the homothety action on a J normal form. So consider a normal form, a J normal form given by the previous theorem. We consider the parameter vector, and the parameter vector is the vector we put in the coefficient of the first branch in this position, the coefficient of another component and the second, so on. Okay, so we obtain this vector, and when we act a homothety element in a J normal form, and homothety is given by this one. In order to keep the Puiseux form, we have to obtain this condition for the branches doesn't belong to the second block, and this condition for the components in the second block, and this condition is just to maintain normalizing this component, and in order to maintain the tangent line, we have to obtain this relation too. We recall if we have more than 2 blocks in the homotety, alpha and gamma are the same. So when we act the homotety in a G form, in a G normal form, we obtain a psi, and if this is the parameter vector associated to the psi, the relations among the coefficient are presented by this expression. If you have 3 or more blocks, the coefficient of the original G normal form are related to the normal form associated to the psi by this relation. And if you have less or equal to 2 blocks, so we have this condition. So remark that if we choose a particular value for alpha, we can normalize a coefficient. Of course, if we have 1 or 2 blocks, maybe it's depend of this relation, we can normalize 1 or 2 coefficients. So in this way, we have this following theorem, the A normal form. If you have a multi-arm psi, multi-arm phi, with a fixed sigma ring and a fixed set of lambda, so phi is equivalent to a psi given by G normal form with parameter vector given by this way, satisfying. If the parameter vector is the new vector, so the psi is precisely the lines. But if the parameter vector is non-zero, then we can choose a parameter to normalize. And we show the first non-zero coordinate in P. In addition, if we have another G normal form, psi prime, with the same sigma ring, the same set of lambda, with the parameter vector given by this way, and normalize the corresponding coordinate, so psi and psi prime are A equivalent if only if the following condition holds according to the number of blocks. If we have only one block, so the coefficients satisfy this relation for a non-zero non-zero complex number. Remark in this exponent, the index associated to the branch we normalize the coefficient is important, appear here. If we have just 2 blocks, the analysis splits in 2 cases according to where is the reducible component with normalized coefficient. If the normalized coefficient appear in a reducible component in the first block, so we have this condition for the coefficient according to the element in the first or in the second block. If the normalized coefficient appear in the second block, then the first block has just one branch, and the branch is given by this one. And the second block, we have several components, and the coefficients are related by this expression. If you have 3 or more blocks, then the coefficient of psi and psi prime are related by this condition, where C now is a particular root of the unit. So, in this way, it's easy to decide if 2 curves are or not A equivalent. And this theorem allows to decide if two curves are or not analytically equivalent. Because if you have a curve with R branches, we can compute the A invariants, the sigma ring and the set lambda, and using this, we can compute its A normal form according to the previous theorem. So given another mole germ, for instance, C prime, we compute the A invariant, the sigma ring and the set lambda for any permutation of the mole germ. If the corresponding invariants are distinct, so C and C prime are not analytically equivalent. But if it's not the case, we consider the subgroup of the symmetric group, so the fixed, they maintain the sigma ring and the set lambda. So the curve C and the curve C prime are analytically equivalent if only if the A normal form for some permutation of psi satisfy the previous condition theorem when we compare with the A normal form of phi. So this allows to solve the analytic classification problem for curves with several branches. Recall we have an algorithm to compute these invariants, so it's manual to do this. When we apply this theorem for the reducible case, that means we in this case the J group is precisely the A1 tilde group. So the previous theorem, the A normal form, gives us this short parameterization. Here, as we have just one branch, the condition about the set L is precisely this one. We have to consider terms T to L to T to J for the J doesn't belong to Lj. So this condition, Lj is empty, is equivalent to say the J doesn't belong to the invariant lambda J. If you fix a sigma ring given by these generators, so the first element here doesn't belong to the lambda G, is precisely the T2n. So we can normalize it. So the A normal form can be rewritten in this way. So if Oj greater than m belong to lambda J, so phi is analytically equivalent to the quasi-homogeneous curve. But if there exists element here greater than J that doesn't belong to the lambda J, we can set lambda, the minimal element doesn't belong to the set lambda, so we can rewrite this normal form in this way, and this lambda is precisely the evaluation of this form, and this lambda is the invariant considered by Zariski and his famous course at École Polytechnique. So this normal form is precisely the normal form presented in the main result in this paper in 2011. For the B germ, we have two distant cases according to the number of block or distant tangent. If you have just one tangent, one block, so the previous theorem, the A normal form theorem, gives us the normal form is given by this one and this one. And if we have two branches, two blocks, the normal form is given by this one. And we write this condition, the 2 doesn't belong to the Lj, or the 1 doesn't belong to Lj, we can recover the result, the theorem, and this paper relate to the classification of the germ. Okay. Recall, as we mentioned, when you fix the topological class, when you fix the Simon ring, for instance, we have a finite number of distinct lambda g, this invariant. So we can stratify the moduli space according to this invariant, according to this discrete invariant, the lambda set. So fixing the semigroup, we can compute a set lambda. So we can describe all curves, all multi-term that admits this Simon ring and this particular set lambda. So this allows to describe the component in the modeling space associated to this invariant. Of course, if you consider the Simon ring and the generic component, the generic coefficient, we can compute the lambda associated to the generic multi-term. So we can describe the generic component of the moduli space, and so we can compute the dimension of it. This question was considered by several authors. For instance, Zariski considered this problem, and Zariski described the moduli space for some topological class in the irreducible curves, and Zariski present a formula for the dimension of the generic component for the associated to the topological class given by the Simon ring generated by n and n plus 1. The norm present a formula, a combinatorial formula, to compute the dimension of generic component for irreducible curves also, but for semi-ring generated by two elements. Ranger compute the generic component and the dimension of the generic component for singular ordinary curves, singular ordinary point. Briançon, Ranger, Mazunov consider this question also. Luengo and Pfister, Grew and Pfister consider the question to determine the dimension of the generic component using the Turinus number. And Gassman and Pohl present a method to compute the dimension of generic component in a particular topological place for curve with several branches. So, if you consider a singular ordinary point, this means C is a curve with R irreducible component, regular irreducible component with tangent with distant tangent. This means we have R blocks, and each block we have just one element. So it's possible to compute, to describe the set L satisfying the star condition. So we have, for the generic case, we can compute, we can describe the LK, and the LK satisfying the star condition is precisely given by this way. L2 is 1, 2, 3, 4. LK is given by this one, so for k greater or equal to 3. So compute. If we compute the cardinality in the normal form, we can obtain the dimension of the generic component for the moduli space, and this dimension is given by this formula, and this formula was obtained by Granger in this paper. And if you consider a topological class considered by Gassman and Pohl, in this topological class, all branches has the same Simon ring, n and m, and the multiplicity intersection is precisely n times m. This is exactly to the example when I present a picture. In this situation, we have just one block, and we have are elements in this block. So in this situation, for this topological class, we can also describe the set L, okay, and we can prove the dimension of the generic component for the n-mod germ in this topological class. The dimension of the generic component of the modular space satisfies this relation. So we can compute this if we can describe the set L satisfying the star condition, except for the case, the irreducible case, and n and m equal to this pair. In this situation, the modular space is precisely a single point, but for another case, this formula holds. If you can fix, for instance, a particular n and a m, we can describe the set L, and in the particular case, to n equal to 2 and m equal to 3, we get this formula for the generic component, the dimension for the generic component for the modular space. Okay, so I think that is. Thank you very much for your attention.
Okay, thank you, Marcelo, for this beautiful talk. And we are waiting for questions or comments. Well, I will start with some question. Now that you have the classification for plane curves, what about the space curve case?
Yes, the first thing is how to describe the topological class in this situation. It's not clear for me, for instance, using the parameterization. But in many other cases, we can compute the invariants. We can compute the set lambda and valuation also. But it's not clear for me how can you describe curves in a fixed topological class, for instance. Maybe if we consider a particular class, for instance, complete intersection curve, or another situation, maybe it's possible, but I don't know in general.
The question is because in a base paper, he considered the case of space curves without any restriction, and he gets some results about them.
Yeah, you're right. For a irreducible case, yeah, you're right. All right.
Okay, we have some questions, starting with Patricio Almiron. He has two questions. Is the homotopy action compatible with each step in obtaining the normal form G?
No, because when you consider the A group, we can eliminate parameters. And the homotopy action, we can, in fact, normalize a coefficient in each step. So, of course, we can, for instance, normalize a coefficient in the beginning of the process, and after that we can remove, and we can normalize another one. So, the idea is eliminate all the possible parameters, and after that we can normalize the coefficient. Of course, we can have many shows to normalize. We can choose not a particular coefficient. We consider the first non-zero coefficient in the A normal form. Okay.
Okay, there is another question. Rafaela Martins.
I think it's a question of Michel Granger.
Oh, Michel Granger. Do we have related results about the set of valuations of logarithmic forms along a reducible?
Yes, thank you for the question. In fact, Poe related the valuation of residues, the model of residues, with the value of the differential form. In fact, we have a kind of symmetry. If you have a value, a residual value, the set of residual value is precisely the Frobenius vector minus the set of the value of Kähler differential. And the Frobenius vector is the conductor minus 1. So it's possible to relate this invariant. These invariants are equivalent. And we use the Kähler differential value in order to obtain another analytic invariant for the Turinus, for instance.
Well, there is a question by Johann Gensmer. Beyond space curves, maybe it would be nice and maybe easier to consider curves on singular surfaces.
Yes, this is a nice question. I think I have to think more about this. Yes, but thank you for the question, Johan.
Patricio Elmiro has another question. Also, what can be said about the structure of the moduli space? For instance, is it connected?
Okay, thank you, Patricio. In fact, here we consider the stratified moduli. Okay, we stratify the moduli space, so we can describe the structure in each component. For instance, for the generic one, and when you consider a fixed lambda g, for instance, in order to obtain this analytic invariant, the lambda g, we have some algebraic relations among the coefficients. So in this extract of the moduli space, the moduli space is described using this algebraic relation.
I think there are no more questions. Okay, let us thank Marcelo for this nice talk.
Thank you, Abraham.
And I invite everybody to go to the coffee break. Please bring your beverage all together. Okay. See you in a few minutes.
Okay.
It's my pleasure to introduce the plenary speaker of this today. He is Professor Jean-Paul Brasselet, and I think that everybody knows Professor Jean-Paul, and he will give a talk on a very interesting subject about Euler. I believe that everybody knows Euler also. And the talk of the subject of the talk is with Euler, a 50-year journey per minute from Athens to São Carlos. And just to say something about Professor Jean-Paul, that he is, as far as I know, together with Sininha, the only guy that has participated of all workshops. And even I didn't participate of all, but he has participated. Very nice. And he is a great collaborator of the Singularity Group of São Carlos. He is a part of the group. So it's a great pleasure for us to receive you, Jean-Paul. Welcome.
Thanks a lot, Marcelo. Thanks a lot for this nice introduction, and thanks to all organizers of this event, which is marvelous. I assisted at many lectures, and that was very, very nice. I enjoy. So thanks to Sidinia, who is master of this event, and thanks to all organizing committee that did this particular event in such a difficult situation in a very, very nice way. Thanks to everybody. So today you are invited to a trip, a journey of in time and in also in space. We will cover 2,500 years. So in 15 minutes, 50 minutes. So it is a 50 years journey per minute from Athens to São Carlos. That will be a very, 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 very elementary talk. And so I think many people could be tired because of this very strong week with marvelous results. So it will be a very quiet and very elementary talk. Okay, so we start with Pythagoras. Pythagoras is well known for the famous theorem, of course, but he is also well known because he was the guy who introduced the tetrahedron, the hexahedron, and octahedron. So the first regular polyhedra, which are polyhedra is regular if all faces are equal, are the same, and for each face, all edges are the same. For example, you have a equilateral triangle or a square. Okay, so Pythagoras was knowing these three basic tetrahedra. The following guy is Theaetetus of Athens. Theaetetus was very young when he was, as you can see on the picture, he is working on his computer, and with his computer, he succeeded to define, to show that there are two other regular polyhedra, which are icosahedra and dodecahedra. Icosahedra has 20 faces, which are equilateral triangle, and dodecahedra has 12 faces, which are regular pentagon. Okay, this has been described by Plato in his very nice, it was a publication by Plato with called the Themi, where Plato describes the five polyhedra, and he gives also relationship with between the polyhedra and, for example, tetrahedra is fire, hexahedra is the cube is earth, octahedra is air, icosahedra is my God, I don't remember, but and dodecahedra is wall. all of this. So you know that Euclid, in his publication, Euclid gives some more properties of this polyhedra, but no, not more. And also you have a guy who will appear later on, which is Archimedes. Later, because Archimedes is more related with Euler formula. Some people say that Archimedes was knowing the Euler formula, but there is no way to know if it's true or not. I put this, so we come from a BC to 1649. So it's a big step in time. And this is Europe in 1649. So it was quite different from Europe now. You see that, for example, Greece, where there was the starting of the story, Greece was a part of Ottoman Empire. Samos is here. I don't know if you see my arrow. Samos is here. Athena is here. And here is Syracuse. Syracuse, where is Archimedes. And we will use this map. We will go in Europe with later on with Descartes, with Euler as well. In fact, we will go to Stockholm, which is here in Sweden. We will go to Hanover, which is here. You see that for the moment, Germany is not unified. It's a lot of small parts in Germany, but they will unify later. Here is Hanover. Berlin is here, where will be Euler, and here is Paris. And you see that the map is well different from now. For example, Poland is much bigger. Austria here is much bigger, and some part of, for example, Scotland is not in UK for the moment, and so on. So you see big differences with the map now. So let's go. Well, I have a problem here. What's up here? Okay, so maybe I will close and come back. I don't know why. Okay, I don't know what happened. Okay, and I come back. Okay, so it's okay. Okay, so now we are in 1649, and Descartes wrote his famous theorem. In fact, he did not publish his theorem. He made when he was young, maybe around 1625. We don't know. And this theorem, he thought it's incomplete. He had to complete this theorem, so he did not publish. But he wrote a manuscript, and he had many manuscripts like that he did not publish. He wanted to finish later, so he had in a box all this manuscript, and inside the box was this theorem: the sum of the angles of all faces of a complex polyhedron is equal to 2 times v minus 2 pi, where v is a number of vertices. For example, you have here an hexahedron with 8 vertices, and he says that the sum of the angle of all faces is 12 pi. He compute. I put only the angles for the visible face because otherwise it will be very complicated to see. Descartes was invited by the Queen of Sweden, Christine, in 1649. Here is Christine is on the left and Descartes on the right. And in fact, Christine wanted to discuss with Descartes more of philosophy, of metaphysics, of religion, passion, things like that. And she invited in September 1649. Descartes came to Stockholm, you have seen on the map. And the problem is that Christine wanted to discuss with Descartes very early in the morning, at 5 o'clock in the morning, but Descartes was working every day till 2 or 3 o'clock in the morning. So it was very, very difficult for Descartes. And it was winter. So it was very cold. And Descartes got a cold. So we are here in September 1649. And Descartes lives in the house of the French ambassador to Sweden, Pierre Chanu, which is important for the following. Descartes got a cold and he died on February, so very few months, 4 months later, and died of Descartes. In fact, here also there is a question, that we don't know. Some people say that Descartes death of Descartes is due to the fact that some priest gave an host to Descartes with arsenic in it, and so Descartes' death was the arsenic was responsible for death of Descartes. So we don't know if it is a cold or arsenic. We don't know. So there is many controversy and many literature on the subject. So Descartes is dead, and the manuscript is not published. And Chanu sends to all the manuscript of Descartes in a safe to Claude Clercellier. Claude Clercellier was a brother of Pierre Chanu's wife. Okay, so he was in Paris, and arriving in Paris, the safe sank in the Seine. Some people say that, in fact, all the boats sank in the Seine, but we don't know. At least the safe sank in the Seine, in the river, and it was recovered only 3 days later. So you can imagine Clercellier had to dry all documents in the safe, and that is one of the reasons for which we don't know if we have all the manuscript of Descartes. Leibniz, that you know as well, comes in Paris in 1672, and Clercellier confides to Leibniz the Descartes manuscript. Leibniz take a copy. He had no photocopy, Xerox, but he wrote a copy of the Descartes manuscript on mathematics called De Solidorum Elementis. And then Leibniz came back to Hanover. In fact, Hanover, I told you, is here in Germany now. And Leibniz died without publishing the manuscript. He wanted to publish the manuscript, but he did not. So the manuscript was on the desk of Leibniz and stayed there. You know, when you receive a lot of documents to see, you don't look at immediately, so Leibniz did not look. During that time, Euler gave this formula. Euler was in Berlin, more or less here. But this is the other story. And I come back to the story of the manuscript. In 1883, so it's 200 later here, 200 years later, Fouché de Carrel, who was French ambassador for Austria-Hungary here, but he came to Hanover because he wanted to publish the work of Descartes and Leibniz. So, and he discovers between Leibniz document, the Descartes manuscript, under the dust that covered them. So this Fouché de Carrel came back to France, to Paris, and he gave to the Ernest de Foc de Jonquière, who was amiral and a mathematician as well. And Ernest de Foc de Jonquière wrote a note to the Academy of Science in which he tells the story, all the story, and he claims that Descartes discovered Euler formula. In fact, I remember the theorem we have seen of Descartes. Here is Descartes, here is Euler, both of them. And the formula you know very well. If K is a convex polyhedron with V vertices, E edges, and F faces, then you have the Descartes relation, the Euler relation, V minus E plus F equal to 2. I have to say now that there is a very good book on the subject with which gives history and proof and also counterexample and so on. And I recommend this book for people interested by all this story of Euler results. Well, so what did Euler? Euler wanted to classify all polyhedra. And he started by classify polyhedra by number of faces. And he discovered that even with the number of faces, for example, here we have hexahedra with 6 faces, and there are many ways to organize these faces. And he wanted to classify, so he wanted to distinguish between them, and he started by distinguish between the number of vertices. 5 vertices, here we have 2 with 6, we have 2 with 7, we have 2 with 8 vertices. And he said, okay, but now I want to distinguish between these 2 polyhedra, which they are 6 faces, 6 vertices, and I want to distinguish these 2. So he looked at the number of edges, and he have seen that these 2 have 10 edges. These 2 have 11 edges. These 2 are 12 edges. So he did not succeed to distinguish between them by the number of edges, but he had, on these examples, the relation V minus E plus F equal to 2. And so he wrote to his friend Goldbach that he wrote a letter in 1751 to his friend Goldbach, saying that I have this formula for all example I can picture, and the Goldbach says that so you have to publish this and to prove this. And so Euler gave a proof in 1753, but this proof is incomplete, is not complete, is not good, in fact. And you can see that in the book I gave you the reference before. But what can be shown is that effectively, as I said before, the Descartes theorem implies the Euler formula. And this is easy to prove. If you take this, for example, this hexahedra here, you can compute the sum of all angles of all faces of the polyhedron with 2 ways. The first way is the Descartes theorem, and the second way is taking each face one by one. For example, this face is a pentagon, so 5 edges, and this pentagon can be divided in 3 triangles, okay? And each triangle has a sum of angles which is pi. So if I have 3 triangles, I have 3 times pi. And the same here, I have 2 times pi because I have a square, and here I have only pi because I have a triangle. And you take the sum of all these, you write the sum for all faces, and in terms of the angles, and you see that when you write this sum, you will have appearing the edges, and one edges is a border of 2 faces. So you have to take this into account, and then you obtain the Euler formula. So it's very easy to prove. It's an exercise to prove that Descartes' theorem implies Euler formula, and many people say that this formula should be named Descartes-Euler formula, but I let you decide. The first complete proof of the formula, out of this fact that nobody at that time have seen that Descartes implied Euler, so the first complete proof was by Legendre, and Legendre was using a so-called Girard theorem, which is a theorem which is a way which is more or less dual from Descartes. And then the combinatorial proof of the formula by Cauchy. And we will be interested in this proof by Cauchy. It's very funny that Legendre was a revolutionary, strong revolutionary, and on the contrary, Cauchy was a strong royalist. He was baron, in fact. So what is the Cauchy proof? Cauchy says, okay, I have a polyhedra which is convex. So it means that for each face, if I put the polyhedra on a face, the polyhedra is completely on the same half space. Okay. For example, if you put this polyhedra on the face ABCD, so you have a plane, and the polyhedra is completely on the plane. And so you can use the stereographic projection, taking a point here, and you take the stereographic projection of the polyhedron, of the polyhedron, yes. And so you obtain this, and then you obtain here a polygon which is on the plane, and each edge, each face, and each up. So here I have a problem again. Oh my God, I don't know what happened. So I have to come back here again and again. Yep. Okay. So, okay. So I have the stereographic projection of the polyhedra, which is a polygon here. Okay. And same number of vertices. Each vertex here corresponds to a vertex here, face and edge as well. So you remove this face F to do this stereographic projection. And then Cauchy says, okay, I have this polygon, a result of the planar stereographic projection. And then Cauchy considers a subdivision, which is a triangulation of this polyhedron, of this polygon. And then Cauchy uses so first of all, he says that the sum V minus E plus F is preserved by subdivision. He shows this. So this is the first thing. And then we will extend the hole, which is, I don't know if you see very well the hole here on the boundary, which is in blue, by means of two operations that I will describe now. But this is exactly the stage that is controversial, and that we will replace in a proof later. So the Cauchy one, the operation 1 by Cauchy is the following. If you have here a hole, which is B, okay, is buraco, okay, so the hole is B, and I can extend the hole to the next triangle sigma by deleting sigma, by deleting tau as well. So I extend the hole. I extend deleting one triangle and deleting one edge. So the sum V minus E plus F does not change. Okay. Again, now the hole is like that. And again, you can extend with the next triangle like that. Okay. A triangle, one edge. Again, so the hole is now like that. Again, I can extend with one triangle, one edge. And each step, the alternative sum, V minus E plus F, does not change. But now you see that I have a triangle here, which is different because it has two common edges with the hole. So I have this picture now. And if I want to delete this, to put this triangle also in the hole, I have to delete one triangle, two edges, and one vertex now. So I have 1 minus 2 plus 1, and the alternative sum does not change. So this is the Cauchy 2 operation, the second operation by Cauchy. And Cauchy says that deleting as in that way by operation 1 and operation 2, all triangles, at the end, I have only one triangle left. And for this triangle, I have three vertices, three edges on one triangle. So I have V minus E plus F is plus 1. But don't forget that at the beginning, you deleted a face of the polyhedra. So you have to add this face. So you have V minus E plus F is equal to 2, which is exactly the Euler Poincaré characteristic of the sphere, okay, of any convex polyhedron. But there is a controversy. This controversy is, I will say a little later, but it comes from the fact that if you start with this hole and you extend the hole on the left here, on the right here, you arrive to this picture. If you arrive to this picture, there is a triangle here that you cannot remove, because if you remove this, you remove one triangle and two edges. So the alternative sum, V minus E plus F, change. okay, is not preserved. I remove one triangle and two edges. So in that way, if I follow this, I cannot prove the formula. So some people made a criticism, like Imre Lakatos, who made a criticism in a book, which is Proof and Refutations. And he explains that the Cauchy proof does not work because you can have these problems. And Elon Lima, which is was a very, very good professor in Brazil, and made very nice books for university, very, very nice books. And in general, I like a lot, but he made a mistake, and I have to say, in this paper he wrote in 1985, he says that, first of all, that's correct, that there are 4 situations that Cauchy did not see. There are 4 situations like that. I hope you can see the hole here on the 2 sides, which is exactly, this picture is exactly the one we had here, okay, the hole on the 2 sides on the triangle here. But you can have also that one, also that one, also that one. That one is okay because I have two vertices, 3 edges, and 1 triangle. So that is okay. But these 3, with these 3, you cannot show that V minus F plus F is preserved. So, and Elon Lima writes a very nice paper where he shows that with deep results, in fact, with homology and homotopy and strong result in algebraic topology, you can show that you can avoid these 4 pictures here. And he writes that, I will translate in English, it's not possible hope to obtain elementary proof of the Euler theorem with the hypothesis that P, than the polyhedron, is homomorphic to a sphere, as did Hilbert Cohn Vossen and Courant Robbins, but Hilbert Cohn Vossen and Courant Robbins, it's exactly the Cauchy proof. So he said, Elon Lima says that it's impossible to obtain an elementary proof with only this hypothesis without deep results of algebraic topology. And what I will do now is to provide to you an elementary proof of the Euler theorem. So first of all, we start exactly as a Cauchy. Okay, so Cauchy, you delete the face here, and you use stereographic projection on the plane. Okay, and then you subdivide, so as a triangulation, and then we stop the way Cauchy proved, and and then we will finish the proof in another way. So we will prove, using only the Cauchy method, that if V0 and E0 denote the number of edges and the vertices of the boundary, okay, on the boundary here, we have this formula for the polygon. V minus E plus F is equal to V0 minus E0 plus 1. We will show this. And this is if you have this, you see very well immediately that you have the Euler characteristic of the sphere, because V0 and E0 are equal. There is the same number of here. Okay, the vertices and edges are in equal number. So V0 minus E0 is 0 plus 1. So you have, for the polygon, which is here, you have plus 1. But don't forget that at the beginning, you deleted the face F, you removed the face F for the polyhedron. So for the polyhedron, you have V minus E plus F equal to 2. So if we show this theorem here, we win. So let's prove this theorem. I think this theorem, well, not I think, I am sure, I can prove this theorem in a very easy way using homology, of course. And that if you have a triangulated polygon like that, okay, and the Euler characteristic total of the polyhedron is equal to the Euler characteristic of the boundary plus 1, even if you have identification of the simplices in the edge, in the boundary. For example, if you have here identification of B1, B2 with B5, B4, okay, in that case, you have 1, 2, 3, 4 vertices, because these two, B4 is equal to B2 and B5 is equal to B1, so you have only 4 vertices, and you have only 5 edges because these two are equal. So even if you have identification of simplices on the boundary, you have this formula. So let's show the theorem. So that is a theorem I proved with Nguyen Thibish-Thuy. Nguyen Thibish-Thuy is professor in IBILS in UNESP in San José do Rio Preto. It's not so far São Carlos for Brazilian metric, I will say. And Nguyen Thibish-Thuy was formerly my student, but she did a postdoc with Sidenia in São Carlos, and then she was appointed as professor in UNESP. And so it's a great pleasure to present this theorem. This theorem is saying using only the Cauchy method, we prove this. Okay, only using the Cauchy method, without any theorem about homology, without using homology or homotopy or nothing, even not using Hauptvermutung. If you use Hauptvermutung, it's easy also to prove this theorem. But Hauptvermutung was later than Cauchy. Okay, to tell the truth, we will use a Vietnamese fisherman net and also a French salad basket. I will explain this immediately, and subtriangulation. So let me show this if I succeed. Okay. I hope you can see that. It's okay, Marcelo, we can see?
Yes, Jean-Paul, I can see you.
Okay.
It's everything all right.
So you see the French salad basket that you take like this, okay? So if you have a planar triangulation, you can lift this in such a way that you have a kind of pyramid, okay? It's nice? Okay.
Sorry, I didn't hear you very well.
Okay, so come back to the diaporama, and so we'll use this way. We'll use subtriangulations, but Cauchy was already knowing subtriangulation, we know that, and he uses subtriangulations. For example, like that, if you have a tau, simplest like that, you can have a subtriangulation, and the alternative sum does not change. V minus E plus F does not change. And the same here, if instead of such a tau, you have a tau like that. Okay, so you have a subtriangulation. Here you are obliged. Here you have a you are obliged to cut in order to have triangles. And in the two cases, the alternative sum does not change. Cauchy was already knowing that. And now I will use my salad basket. I take a triangle inside, okay, any triangle inside, but not touching the boundary. And then, as I did for the salad basket, we will lift the triangle, and all the polygon follows, the triangulated polygon follows. The point, the vertices which are close to the boundary, they don't go too high, and the vertices which are closer to the triangle you choose are higher. Okay, so you have this kind of pyramid, which is exactly you have of course a bijection between your pyramid and the polygon on the bottom. That's clear. So what do? You cut the pyramid by parallel planes going through all vertices, x1, x2, and then you create a subtriangulation compatible with the planes. So you cut your pyramid, and so you have new vertices, and you have new edges are, of course, new triangle. But as you take a subtriangulation, the alternative sum does not change. V minus E plus F is the same. And now you can go from this, so you create a hole, taking out this triangle, and you extend your hole plane by plane going down, and at each step you have a kind of belt, okay, and it's clear, it's easy to see that you have only the operation 1 and 2 by Cauchy to go down from one plane to the following plane. So if you do like that, okay, so you remove the simplex which is on the top. So you have V vertices, E edges on one less face because you remove this simplex. Going down to one plane to the following plane and using the Cauchy operation, this alternative sum does not change. And you arrive at the last one, and the last one you have V0 minus E0. The number you have only vertices on edges because, of course, there is no face when you arrive on the bottom. So you have this theorem, which is very easy to prove using only the Cauchy method. And so it's very nice, and we enjoy this nice theorem. Certainly, it is possible to show in another way, but this way is using only the Cauchy method, and that's very important. So let's give you. I have to check the time. I have 40. So okay. Oh my God, I have till 40. So it's okay. So we will use also a method of cutting surfaces with scissors or knife, as you wish. That was given by Alexander Veblen in a seminar, and he did not publish this method of cutting surfaces, but in fact, it's not very complicated. You will see this method of cutting surfaces by Alexander Veblen, which is very nice. And subtriangulation means that you can subdivide, and the alternative sum does not change. This we know already, but we know for linear simplices, but of course it goes always if you have curved curves. So you will understand very well immediately on the sphere. So take the sphere. Take any triangulation of the sphere, any triangulation. For example, I picture only one triangle because if I picture all, it's difficult to see. But take this triangle. And now I take three curves, which are I take equator, and I take these three half meridian, gamma 1, gamma 2, gamma 3. Okay? Gamma 2 cut here my triangle. So I can create a subdivision such that these three meridian, half meridian, and the equator are the triangulation will be compatible with them. Okay. For example, here it's suffice so to have this edge to incorporate this edge, and then I have here a subtriangulation of my triangle, which is compatible with gamma 2. Okay, so this here also is a simplex edge. So I have this, and then I take my scissor or my knife, and I cut according to the three meridians, half meridians. So of course, now I have here identification of this simplex with this simplex here. So if you project on a plane, you have this picture, and we have identification of this with this. Okay? And I have the same for gamma 1, for gamma 2, and for all gamma 3, because I have exactly the same situation. If I look at gamma 1, it's clear that I have always the same number of vertices and the same number of edges on the blue, on the red, and on the black one. And I have, apart this, and the North Pole, which appear 3 times here, okay? But this is only one point because I have identification. Now I have identification on the boundary. The vertex n is common to all curves, so you have only +1 for the number of vertices on the boundary. For each curve, we have the same number of vertices on edges. Oh, sorry, there is a mistake there. Edges. So v gamma I minus gamma I is 0 for the 3. So V0 minus E0 is +1, which is only the north pole. And then, using our theorem, V minus E plus F is V0 minus E0 +1 by the theorem, so it gives +2 for the sphere. So Euler point characteristic of the sphere is computed only computing the number of vertices on edges on the boundary of this figure. You don't look at what appears inside. You don't need at all. Of course, you can do the same for many pictures. Here for the torus, I insist on the fact that you take at the beginning any triangulation of the sphere. Here you take any triangulation of the torus. You take a meridian, you take a parallel, and then you take a sub-triangulation compatible with them, and then you cut, and you obtain a very picture that everybody knows, but usually we have the regular triangles and the parallel and so on. But here there is any triangulation, but as you cut for the sphere in the same way that for the sphere, you have identification of this with this, and this G with G, and so on. And if you count the number of vertices on edges of the boundary, you have -1. So it gives for the torus 0. So it's very interesting to see that Euler point characteristic of the torus, you need to look at only the boundary of this picture obtained by cutting. You can do the same for the torus with genus G. Okay, for example, here I did for 2 and for 3, which is very nice monkey here. And it's a pity that when you give a lecture like that, you cannot see if people are smiling or laughing. And when you are in an amphitheater, you can see people laughing, smiling, and so it's really more difficult too. I hope you are, if not laughing, at least smiling. So now you can do also for non-oriented surface, like the projective space. You know that projective space you can represent by a sphere with identification of symmetrical points symmetric relatively to the center. So any triangulation of the projective space will be symmetrical relatively to the center of the sphere. And you can choose only one hemisphere. This you know very well. So I take any triangulation of the projective space. I cut here by the equator, and then I take only the upper part. Okay, I have identification of points diametrically opposite on the equator, and then you project, and then you have this picture. And then you compute only vertices and edges on the boundary, and you get for the projective space +1. Okay, so this is very easy. You can do the same for the Klein bottle. I will not. I will go more rapidly. You take one parallel here, one parallel on this on the blue one, and then you have this picture. Always with any triangulation of the Klein bottle, you can show that you have V0 minus E0 is -1. So for the Klein bottle, Euler characteristic is 0. And also a singular, we have no singularity for the moment. So the Pinchet torus, of course, I cannot give a lecture without Pinchet torus. If you take the Pinchet torus, you take here any triangulation. Of course, as for the previous pictures, I pictured like that. But this is not a triangulation. This is only to figure out how is the Pinchet torus. So you take any triangulation of the Pinchet torus, and you cut, along this equator here, A, and then you have the Euler characteristic of the budget torus. Okay, so this is Cauchy, only Cauchy, and I agree. I use this cutting surfaces way by Alexander Veblen, but it's not. I think it's very interesting. It's very nice to show like that. So we continue our trip with always with Euler, continuing with Euler and Poincaré, generalized Euler. You know, if you have a finite polyhedron and Ni, the number of high-dimensional faces, you have the formula by Poincaré. And you have the Poincaré-Hopf theorem that Poincaré proved for in case of surfaces, n equals 2, and Hopf for all dimensions. It's I look at Poincaré papers, well, it's more or less understandable. It's possible to understand more or less, but it seems very strange that Poincaré generalized the Descartes-Euler formula for any dimension, and then he wrote the Poincaré-Hopf theorem only in dimension 2. And that he did not show in a whole dimension. So it's very strange for me. Okay, so as we are working with singular variety, some people know very well what I say now, that in a singularity theorem, the Poincaré in singular variety, the Poincaré-Hopf theorem is not always verified. For example, here, the Poincaré-Hopf theorem is not verified. Why? Because you know that in a three-dimensional space, the index of a point, singular point of a vector field, it depends only on the vector field on the sphere. And here you can imagine that in fact you can forget that it is a singular, and you can put here the torus, and you have the continuous vector field on the torus whose index is 0, no singularity. So here on the boundary, it's entering and going outwards, so index is 0. And if I take this vector field, which is going outwards, all the ball in three-dimensional space, okay, it's going outwards. So in that case, the index is +1. And as you know, as we have seen before, the Euler-Poincaré characteristic of the torus is +1. So the Poincaré-Hopf theorem is true for this vector field and is not verified for this vector field. So the Poincaré-Hopf theorem is not verified for all vector fields. And this is a very nice result by Marie-Hélène Schwartz in 1965. She shown that the Poincaré-Hopf theorem you can recover for a singular variety equipped with a Whitney stratification, and the Poincaré-Hopf theorem is true for radial vector field, and I have to explain what is radial vector field. It's very easy and very fast. If you have a vector field on a stratum, V alpha, here, V alpha is this curve, and with a singular point here, point A is singular, and you take your vector field V, okay? You can extend the vector field. Of course, I made a simple picture. You can imagine that V alpha is inside a more complicated singular variety with strata V beta and so on. And in fact, using condition A, Whitney condition A, you can construct a parallel vector field here, and you can show that the parallel, if you take strictly, if you have in some metric, of course, Euclidean metric, so the parallel vector field, you can show that the angle of the parallel vector field on the tangent space to the point you consider, to the strata of the point you consider, is small. So you can project, okay, it's never perpendicular. So you can project and the vector field is not 0. This is a Whitney condition A, which says that. And then you can also consider a transversal vector field, which does not depend on V. by Whitney condition B, you can show that this T, which is transverse to V alpha, okay, and this exists, and this is 0, of course, along V alpha, but it's growing 1 with the distance to V alpha, okay? And so you sum up these two vectors, the parallel one and the transversal one, and you obtain in red a vector field, which is the sum of the parallel and the transverse, and this is the radial extension of your vector field V alpha, okay? V alpha here, V can have any singular index. And I recognize that the name VRAD is not so I use with Marie-Anne Schwartz, but it's not radial. It's a radial extension of a vector field on V alpha. And so using this stratified radial extension vector field, you can see that Euler Poincaré characteristic of X of the singular variety is equal to exactly the sum of indices of this stratified radial vector field. So you have a Poincaré-Hopf theorem in the case of singular varieties. And this is a very nice result from Marie-Anne Schwartz. In fact, she shown not only for radial vector field, but also for airframes. And this provides the so-called Schwartz classes, which are in the cohomology of M modulo M minus X. M is the ambient smooth manifold in which you have this complex analytic variety X, okay? So you have the cohomology Schwartz classes, which are obstruction to the construction of stratified frames, tangent to a complex analytic variety. Later on, in 1969, Deligne and Grothendieck conjecture existence of homology chain classes for complex algebraic varieties, and this was shown by Macpherson in 1974. He proves the conjecture and defines homology classes. In some lectures previously in this congress, you had these Macpherson classes, and Macpherson classes are for all alpha which are constructible function on X, which means that constructible function can be relatively to a stratification or a triangulation. For a triangulation, for example, it means that there is a triangulation such that alpha is constant in the interior of each simplex. And one of the ingredients is the local Euler obstruction that we will see now. But let's continue historically. In 1979, Marie-Anne Schwartz and myself, we show that the Schwartz classes here are the same than the Macpherson classes for the function 1 on X, for the constructible function 1 over X. And via Alexander duality, there is Alexander duality is isomorphism between this cohomology, which is cohomology with support in X, if you wish, and the homology of X. There is a isomorphism between both, which is Alexander duality. And you know that the classes are called now Schwartz-Macpherson classes. They appeared in some lectures, previous lectures. And in previous lectures, you have seen also the way to define the local Euler obstruction, and this local Euler obstruction here, that we will speak now. It's always continuing our trip with Euler. I have to show what time is it, so I have, my God, no more, many times. So the Nash transformation you have seen, that the Nash transformation here, if I take this picture, if you take the regular part of X, on the regular part of X, if X is n-dimensional in M being m-dimensional, okay? So you have here the Grassmannian of n planes in Tm, and you have a section gamma going from X, regular part of X to the Grassmannian, and to each X in a regular part of big X, you have the tangent plane. This is n plane in the M plane. So you have the Nash transformation that you have already seen in other lectures, and you have also seen the tautological bundle E over the Grassmannian that you restrict to X tilde. X tilde is in the Grassmannian space, and so you restrict, and you have here the Nash bundle. The Nash bundle is the set of x tilde is a set of n-planes, and e tilde are vectors in these n-planes. I will go directly here in this picture to define, to show one theorem is and here and to define Euler local obstruction. First of all, with Marie and Schwarz, we shown that if you have a witness stratification and a stratified vector field on a part A of X, then it lifts, then this vector, you see here each point X, for each point X, you have the tangent to V alpha, to the stratum of X at point X, okay? And so it's a stratified, so V of X belongs to the tangent plane to V alpha. And you can lift this V in a V tilde, in a section of E tilde over inverse image of A. For example, here, if you have this cone, you have a vector field going outwards the ball of index +1 here, okay, but it going outwards, it is stratified. What is important is stratified. And then you can lift. What does it mean? It means that for X, for each X tilde is a point over X, okay? For each X tilde, you can define V tilde of X tilde. And V tilde of X tilde is a triple point X, which is new image of X tilde, the n-plane X tilde at X, and V of X, which belongs to the tangent space to the stratum V alpha of X. Okay, so you can lift V as a section of V tilde. And you can do that, for example, if you have here a vector field going outwards the ball, so it has index +1 here in the ambient manifold. You can lift as a section of V of P tilde here of E tilde over the sphere, because here there is no singularity, so you can lift over inverse image of the sphere intersection X, and you compute the obstruction to fill inverse image of B epsilon intersection X. And the local Euler obstruction is exactly this, the obstruction to fill inverse image of B epsilon intersection X, okay? So exactly, in fact, Euler local obstruction has been defined by Macpherson. You have seen in previous lectures as well. And our theorem definition, it's a theorem which says that you can compute a local Euler obstruction exactly as I did now. It means that it's obstruction to fill inverse image of X intersection B epsilon as a section of E tilde, knowing V tilde on the boundary of this. Okay, so you want to fill inside, and so it is obstruction to fill. The local obstruction does not depend on all choices, and you have a proportionality theorem, which is very important, which is very useful, and some people use as well. The fact that if you have a vector field which is not of index +1, but any index here, then the index here, the obstruction to fill, will be the Euler obstruction of X that we have seen times the index of your vector field V alpha. Okay? Well, in fact, there is a Letézier formula that you have seen also in previous lectures, which compute Euler obstruction in terms of multiplicity of polar varieties. So you have here, I think my time is quite over. So you have this formula that you have seen, and which is very useful, very used by people, with an example which is a Whitney umbrella, where you can compute by this Letézier formula in terms of multiplicity. It's easier to compute by their formula than computing obstruction to fill, as I said, by the theorem I have with Marie and Schwarz. You have seen also this Lefschetz type formula, which was Pepe, Lay, and myself that you have seen that Euler obstruction can be computed in terms of Euler obstruction of all strata going to 0, and in terms of this Euler Poincaré characteristic, Euler is always there. And also, you have seen Euler, this formula, Euler obstruction of a function at the point. In fact, if you have a function with an isolated singular point at 0 of x, okay, an analytic function, then the gradient vector field makes a small angle with the tangent, so you can project, and this is more or less the idea. So you can compute the Euler obstruction for this vector field here, and then you have this formula. Euler obstruction of a function is Euler obstruction of at 0 minus this, but here, instead of having L, which is a project linear form here, in that formula you have here f minus 1 of 0. Okay, so many, here is a picture, and many people wrote papers, we will see now. In fact, Nivaldo gave a relation between Euler obstruction of a function and the Bruce Roberts index. Also, Bruce Roberts index was mentioned in a previous lecture, so all this is well related. And Dutertre and Gruglia, they define what I will call the B number. Allow me to define as a B number. Oh my God, I have again the same problem. I have to show and to come back here. Okay, so and they define, they show Legreal formula for this B number, which is here, in terms of morphification, which is very nice formula. In fact, there is a lot of papers. I give rapidly a bibliography. For the first part, we have 2 papers with TUI, with UNT-based TUI, that they are here. And for the second part, it's fantastic. There are 28 papers, articles, written by São Carlos researchers, either alone or with co-authors. And this is, I looked at all papers on Euler obstruction, and these 28 papers are 36% of the total number of papers. So it's fantastic, the production of papers by people in São Carlos on ICS, on discriminant, on determinantal, torus action. There is a lot, and I have no time to discuss all of them, of course, but you can find in the PDF, in the announcements, if you click on the PDF, you will have all these papers with abstract of each of them. So you will see all this. It's fantastic. And all these are written by some people in São Carlos, and alone or with co-authors. But I did not mention papers by the co-authors alone. I mentioned only the papers where there is at least an author from São Carlos. So it's fantastic. Papers on obstruction, Euler local obstruction of the space, on a space, local Euler obstruction of maps, and with many papers by all people. I will mention all people now because I think it's very fantastic. So the B number appear here, okay. And so it's all abstract. You can copy this, but fortunately, just click on the PDF in the announcement of this lecture, and you will have not only the papers, but also the abstract of all of them. And I have to thank a lot. First of all, my co-author TUI from UNESCO, and also for the second part of the lecture, Euler. I forgot to thank Euler, of course, Euler, and Descartes as well. And Bruna, Camila, Diana, Daniel, Eliris, Graziele, Hélène, João, Juan, Luis, Marcelo, Cédinia, Miriam, Nancy, Nicola, Nivaldo, Roberto, Rodrigo, Terry, Thais, and Victor Hugo. So thanks a lot. Muito obrigado pela atenção. And vamos festejar os, we will make a feast for the 30th anniversary of workshop of São Carlos.
Thank you very much, Jean-Paul, for your talk. Very, very interesting travel during all these years talking about Euler, characteristic and Euler obstruction. Thank you very much. We are checking. In fact, you gave a so clear and interesting talk that we have no questions to ask you because there is a question from David Trotman. How
Yes.
does one know about Veblen's talk?
About?
Veblen's. I don't know, V-A-B-L-A-N.
D-L-A-N-L? I don't know.
Oh, we don't know. Sorry, David.
I will discuss with David.
Okay, you can discuss with him in Marseille. Great. Please tell us later. Okay.
Can you see me?
Yes, I can. Very clear.
Okay, so I can open.
Yes.
Can you see me?
Please, Jean-Paul.
I will feast the second anniversary.
Wait just a second.
Yeah.
Because we are going to enter everybody in the organizing committee together with you.
Okay.
Also
All people.
yes.
All people attending. All
Okay.
people attending and organizing committee and everybody.
Yeah, hello, Cidinha. Hi, Alex. Hello, Davis. Constantino. And here with Soraya also. So,
That's very nice.
I cannot see you. I cannot see me.
I see you. I see you also.
Okay, so you see me. That's the most important.
Yes.
Okay, so can I?
Please.
Okay.
Yes.
Oh. Thank you.
Santé!
Saúde.
Saúde!
Saúde!
Everybody.
Muito legal. Obrigada, Jean-Paul.
Thank you. Oh, I can take a little more.
Yes.
And I'm so glad to have you here, Jean-Paul Brasselet, giving this talk in the closing session of our workshop. It was very nice to have you here with us. Thank you very much for this wonderful talk.
Okay, so I want to thank, as it is true that it is the last plenary lecture, I want to thank in the name of all people around the world, looking at you, you're looking at these marvelous lectures we had during the week, and also the lectures we will have now. And so thanks for the organizing committee, which made in a very nice way. We had a lot of complex situation, but you succeeded in a very, very good way. And also thanks to the scientific committee, and thanks to Sidinia, special thanks to Sidinia, thanks to everybody. And Santé.
Santé. Saúde. And before we announce today's talks in the parallel session, I wish to thank all the participants which attended this event. And I would also like to say a special thanks to my colleagues here for the organizing committee to be with me and with Miriam in this conference. Since for 3 months, we are preparing this to all of you. And this edition will be registered in our minds. That's a fact. Okay, so see you in 2 years, hopefully. Here in São Carlos. We wait everybody. And now I give
Thank you. I give the word to my colleague Thais, which is going to present the parallel talks.
Thank you. Thank you.
Thank you.
Thank you very much, Alex.
Thank you, Alex.
Thank you.
Thank you.
Thank you to everybody.
So thank you to Alex and to everyone. And it's a pleasure to me to introduce the last parallel sections of the workshop. And the first one will be Juan Antonio Moya Perez from Universidad de Valencia, Spain, that will talk about finite C0 determinants of real analytic map germs with isolated singularity. And also Samuel dos Santos from IBIUS, Unesp, Brazil, that will talk about geometry of bifurcation sets of unfolding of functions with singularity A3, A4, and D4. After, we will have Bárbara Carolina de Lima Pereira from UFSCar, Brazil, that will talk about the Bruce-Roberts number of a function on an isolated hypersurface singularity. And Tito Medina Tejeda from ICMC Brazil, that will talk about extendability and the boundedness of invariants on singularities of wavefronts. We will have a little break, and after the last parallel talk of this afternoon and also of the workshop will be Dimitri Kerner from Ben Gurion University of Israel, that will talk about CR for CR-LIP trivialization of equi-resolvable families of isolated singularity. Thank you very much.